This video is about prime, superprime, and composite numbers. The intent of the video is to show how a very simple block model, such as we have here, can explain prime numbers, and also to explain why prime numbers are important in mathematics. We can use counting blocks to explain prime numbers, the superprime number, and composite numbers. Now, with our prime numbers, one block could represent an apple. It could represent a bicycle, 2 blocks, 2 apples, 2 bicycles. Now, notice that there are no blocks here that represent 0 bicycles. There's no blocks here that represent negative bicycles, nor are there any blocks here that represent fractional bicycles. Now for a basic definition, a working definition of a prime number. A prime number can be considered as any counting number that can't be divided evenly by any other number except for itself. There's better definitions around. For example, a prime number could be defined as a counting number that can only be divided by 1 in itself, or conversely, you could say a prime number is a counting number whose factors are only 1 in itself. When I hear the word factors, I immediately think of a multiplication table. And next graphic I'll show where you can find prime numbers and composite numbers on a multiplication table, the composite number being composed of prime numbers. Prime numbers can only be found in the one-time table. I highlighted the one-time table in pink. The remaining area of the table I've highlighted in yellow. Composite numbers can be found in the yellow area, but prime numbers will never appear in this yellow area. My preference for a multiplication table is to represent the numbers by rectangles or squares. The rectangles and squares will have different dimensions and different orientations depending upon what it represents. They correspond with the counting blocks. Right now, I would like to illustrate the divisibility requirements of prime numbers. Let's start with 4. Here, we're representing 4 by a 1 by 4 rectangle. The factors are 1 and 4. But notice we could form a square, 2 by 2 square, and we have another factor 2. Therefore, it's a composite number. Now let's go back to 2. And this is definitely prime because it can't be divided by any other number. 3. Prime can't be divided by any other number. 2 doesn't work. 4 we did. 5 can't be divided by 2 nor 3. Now, this all seems pretty straightforward. Let's do 6. One more block, okay. And again, with 6, we can see that we can reconfigure the rectangle to form a 2 by 3 rectangle. Definitely composite. Now let's go back to the question of superprime. Prime is defined as a number which can't be divided by any other number. But if 1 is prime, then 1 divides evenly into 2, it divides evenly into 3. So now 2 and 3, well, we could call them sort of prime. But the best way around it is to define 1 as neither prime nor composite, and we'll just call it superprime. Finally, I'd like to illustrate how you can use prime numbers in mathematics. And here we're adding fractions, and the problem is to determine the lowest common denominator. So the first question is, what is the common denominator for 2 and 4? First we ask ourselves, do 2 and 4 have any common prime factors? They do, 2. So therefore we're going to build 2 rectangles with a base of 2, and we can immediately see that 2 is divisible into 4. Proof: 2 times 2 is equal to 4. The next one, 3 and 5. Do they have any prime factors in common? They don't. So the only way to solve this problem is by multiplying 5 by 3, filling in the rectangle, and multiplying 3 by 5. And we could see that these rectangles, I didn't fill them in, but we would see that these rectangles contain 15 blocks each, so 15 would be the common denominator. Simple multiplication of 3 times 5. Now, one more example. What is the common denominator for 6 and 9? Okay. It does have a common factor, 3, so that's going to be the base of our rectangle. We have a 2 by 3 rectangle representing 6 and a 3 by 3 square representing 9. And we can see that if we double the height of this rectangle, we'd have a rectangle with an area of 18. Or if we tripled the height of this rectangle, again we would have a rectangle with a total count of 18. So 18 would be the lowest common denominator. Thanks.